Okay, so let's go ahead and look at the other two compounds in example 5. So let's start off with aluminum oxide. I'm going to show you how to do this. Once again, both methods. You choose whichever method you like. Aluminum is positive 3. Oxide is negative 2. We need at least one of each. If we put 3 plus here and 2 minus there, we can see that this does not equal 0. So we need some more negative charge, right? Well, the mistake that a lot of students make will do this. They'll put negative 1. Well, you can't change the charge of oxygen. If you're going to add another oxygen atom, it has to be in the form of negative 2. So now obviously we have more negative now than positive, so we need to add another aluminum. But we can only add aluminum in terms of positive 3. So to some, they're like, oh my goodness, I'm going back and forth, back and forth. And you're right, a little bit. But finally, if I add one more oxygen, this now makes negative 6 on this side and positive 6 on this side. And so now our charges cancel out to be 0. So if I take a look at how many aluminums it took 2. And how many oxygens? 3. You could have also figured this out using the crisscross method, which, real quickly, the 2 would move down here to be the subscript for aluminum, and the 3 would go down there to be the subscript for oxygen. Comparing our subscripts, can those be reduced any further? No, they can't. And so that would be the formula. Now, so far you might be thinking, okay, I'm thinking that the crisscross method is probably the method I want to use. And to be honest, that's totally fine, as long as you understand why it works. But you need to make sure that you always check to see if the charges can be reduced. Like in this last example, manganese. Manganese is positive 4 based on the Roman numeral, and sulfide is negative 2. If I do my T-chart, 1 manganese is positive 4, and 1 sulfide is negative 2. I need 2 sulfides in order for that to cancel out the positive 4. So based on the T-chart method, MnS2 would be my formula, and that's correct. But if you did the crisscross method, you would have done Mn as a positive 4, sulfide as a negative 2. The 2 goes down there, the 4 goes down there, and so you might have gotten Mn2S4. And sometimes students might not have seen that and forget to reduce the subscripts. So you need to make sure, if you're using the crisscross method, always check your subscripts. The T-chart method might take a little longer, but you'll never get the wrong answer. Now, what if I give you the formula and ask you to write the name? Most ionic compounds are binary, meaning that they only have 2 elements, and it's usually a metal or a nonmetal. Ionic compounds are named simply by taking those ion names that we learned in the last video and just putting them together and removing the word ion. So for example, if we take a look at NaBr, well, Na is the sodium ion, Br is the bromide ion. We just remove the words ions because now they're in a compound. The name becomes sodium bromide. For CaF2, the cation is the calcium ion. The anion is the fluoride ion. You notice how I don't put any indication in the name of how many. I'm just simply saying, what's the name of the cation? What's the name of the anion? That's it. You don't have to indicate the quantity. Same thing as before, remove the word ion and you have calcium fluoride. Once again, watch the spelling of fluoride. Al is the aluminum ion. N is the nitride ion. Remove ion and you have aluminum nitride. This also works if you're working with polyatomics though. Sr is the strontium ion, but OH, that's the polyatomic ion hydroxide. We're still going to do the same thing we did before. Remove the words ion, and you have strontium hydroxide. Once again, the number 2 is not indicated anywhere in the name. Now, what happens if you're asked to name a compound, an ionic compound, that has a transition metal in it? We have to put that Roman numeral, right? But how do you figure out what the charge is? We're going to need to do a little math. So let's take a look at some examples. If we take a look at this first compound here, let's name the ions. Well, what's the name of the cation? It's iron, but it's a transition metal, so it's iron something. And then what's the name of the anion? Chloride ion. We just removed the word ion. So it becomes iron something chloride. How do you figure out what the charge is here for iron? Well, we could do it one of 2 ways. If we decide to do the T-chart way, we know we have iron. We know we have chlorine. And based on the formula, it's telling us that 1 iron cancels out 2 chlorines. I get that from the subscripts. I know the charge of chlorine is -1. So what then must be the charge of that iron ion for it to cancel out those 2 -1 chlorines? It must have been +2. And so therefore, the Roman numeral is 2. You could also do a reverse crisscross as well. So you're probably guessing how this might go. If we take a look at FeCl2, reverse the subscripts back up to be charges. The 1 goes back up to the chlorine to be -1, and the 2 goes back up to iron to be +2. The only thing you have to make sure you check is to make sure that, is chlorine actually a -1? It is. You have to check that because maybe the subscripts were reduced, right? So you need to make sure that that wasn't done. Let's look at the other 2 examples here. Let's look at Cr2SO3 That looks really difficult, but don't let that worry you. Go back to your rules. Name the cation. What's the name of the cation? Cr is chromium. And I notice chromium is a transition metal, so it's going to need a Roman numeral. SO3, yeah, there's 3 of them, but it doesn't matter. What's the name of the anion? SO3 is sulfite. So it's chromium blank sulfite. Now we just have to figure out what that Roman numeral is. We can do reverse crisscross or the T-chart. If I do reverse crisscross, the 2 goes back up to be the charge for sulfite, -2, and the 3 out here goes back up to be the charge for chromium. Just check. Is the charge of sulfite actually -2? It is. So that means this was not reduced, and therefore the charge of chromium is indeed Roman numeral 3. But let's take a look at this last one. This last one, name the cation. Mn is manganese. It's a transition metal, so it's going to need a Roman numeral. We'll come back to that in a second. O is oxygen, but the name of that is oxide. So we name the cation and we name the anion. Now, if I were to do the T-chart for this last one, we have our 2 ions here. According to the formula, it takes 1 manganese to cancel out 1 oxygen. If I know oxygen's -2, that tells me that manganese is +2. And therefore, that's the Roman numeral. But if you were doing the crisscross method on this, you might have gotten a mistake and said, okay, we have MnO. The subscripts are assumed to be 1. That means 1 goes up there to be -1 for oxygen, and 1 goes up there to be +1 for manganese. Oh, manganese is a +1. But hopefully you would have caught, well, wait, hold on. Oxygen's not -1, it's -2. This must have been a case where it was reduced, right? So you have to check that. So the T-chart, once again, the T-chart method's never going to steer you wrong. The crisscross method is faster, I admit, but it does have some room for error, and you need to make sure you're watching out for those mistakes. All right, let's look at some examples here. I'm going to do a few, but then I'm going to pause and let you work on some on your own. So on the left side, we have formulas, asked to write the name. On the right side, we have names, asked to write the formulas. Let's do 2 of each, and then I'll let you do 2 on your own each. All right, let's look at FeSO4. I'm asked to name that. So how do we do that? Name the cation. Fe is iron. It's a transition metal, so it's going to be iron something. Then name the anion. What's the name of the anion SO4? Sulfate. Now I just have to figure out what the charge is for iron. It takes 1 iron to balance out 1 sulfate. And since sulfate's -2, iron must have been +2. Let's do one more. This one down here. Name the cation. The cation is aluminum. I do not have to put a Roman numeral because aluminum is not a transition metal. OH. There's 3 of them, but I don't care. What's the name of the anion? Hydroxide. All right, let's go ahead and do 2 examples on the right side. Given the name, we have to write the formula. Strontium carbide. Well, strontium is Sr, and carbide, especially IDE, that just comes from the element carbon. Whether you do the crisscross method or the T-chart method is up to you. I'm going to go ahead and do T-chart. SR and C. Strontium has a positive 2 charge. Carbon is either one of those elements where it's either positive 4 or negative 4. But depending on the situation, you can figure out which it should be. Since strontium's the positive, carbon must be the negative, and so it's negative 4. If I have just one of each, you have positive 2 and negative 4. That doesn't cancel out to be 0. I need one more strontium in order to make it cancel out to 0. And so, my formula would be Sr2C. If you did the crisscross method, make sure that this was one where you had to reduce the subscripts. Alright, what about this second one? Ammonium chloride. Well, you may be saying, well, I know what chloride is. Chloride is Cl negative, but what the heck? I've never heard of ammonium. Ammonium is actually one of the rare polyatomic ions that's positive. Most polyatomic ions are negative, but NH4 plus is ammonium. If I have one of each of these, the positive one from ammonium will cancel out the negative one from chlorine. We just need one of each. So I'm going to write out ammonium, which is NH4, and then write out chlorine. Go ahead and pause the video and see how well you do on the other two for each side. Alright, let's check our answers real quick. On the left side, we have potassium oxide and aluminum oxide. Both cations are not transition metals, so no Roman numerals necessary. On the right side, zinc bromide is going to be ZnBr2. Even though zinc is a transition metal, it doesn't have a variable charge. We talked about this in a previous video. Zinc is always going to be +2. So notice no Roman numeral was given. We should always know zinc will be +2. For the last one, calcium phosphate, that may have been a little difficult for you, but as long as you're able to understand calcium is Ca with a 2+, and phosphate is a PO4 with a 3-, we could have figured out, doing our T-chart, or crisscross, whichever, that we needed 3 calciums to balance out the 2 phosphates. Anytime you have multiple polyatomic ions, you have to put the polyatomic ion in parentheses, and then put the quantity on the outside. Alright, this last slide will wrap us up for ionic compounds. One exception we want to be aware of is a hydrate. What is a hydrate? A hydrate is an ionic compound that just happens to have a certain number of water molecules attached to it. To indicate how many water molecules, we use Greek prefixes. Those prefixes can be found here on the right. Most of these I'm hoping you're familiar with, such as mono for 1, di for 2, tri for 3. There's also some others that you are probably familiar with, such as hexa for 6, penta for 5, and octa for 8. But there are some ones that probably are new to you or maybe not as common. Tetra, for example, is what we'd use for 4. Hepta we use for 7. Nona for 9. And deca for 10, such as decade. So, how do we name these hydrates? Well, the ionic compound, or the salt, we name just as we normally would. But then when we go to name the water part, which notice how we show it's attached, the number of waters gets named using the prefix, and then instead of saying water, we say hydrate. So the name would be copper 2 sulfate pentahydrate. Once again, the ionic compound is known as the anhydrous salt. That's the part without water. So let's just do one other example. What if I asked you to name this? Alright. First, name the ionic compound how we normally would. That would be magnesium sulfate. Then, indicate how many waters you have. 7 is the prefix hepta. And then instead of saying water, we would say heptahydrate. Alright, that wraps up ionic compounds. We'll see you in the next video for section 4, which starts to look at covalent compounds.